So let us begin with the incomplete proof that we were doing in the previous um, session, and we did up to that point that when X is one of the elements I1, I2 dot 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 ik it, but X does not belong to J1, J2 dot 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 jk, then we have already proved in the previous session that alpha beta of X is equal to beta alpha of X. Similarly, so those after I upload the video in the YouTube, if a student starts seeing the video from this particular part, he will not be able to understand, because the previous portion of this particular proof is in the previous video. So he has to see my videos of permutations in sequential manner, one after another. Unfortunately, I am unable to complete the entire proof in this by using this trial version of Zoom. Similarly, if X is one of J1, J2 dot 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 jk, then obviously that X will not belong to I1, I2 dot 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 it. And if it is so, then since X is one of J1, J2, jk, and it is not belonging to I1, I2, it, because the two cycles are disjoint, just as above we can show that alpha beta of X will be equal to beta X, which is beta alpha of X. We can show this, isn't it? Now, so with respect to my previous example, when I started solving this, I started proving this particular theorem, I considered actually two cases. One of the case was that my elements X is neither belonging to the cycle I1, I2, it, or nor belonging to the cycle J1, J2, jk. In that case, we showed that alpha beta and beta alpha are same. In the second case, we considered two subcases. In the first subcase, we considered that your element X is any one element from the first cycle. We showed that in this case also alpha beta equals to beta alpha. In the second subcase, we have shown that when X is any element from the cycle J1, J2, jk, then also alpha beta equals to beta alpha. So alpha beta is equal to beta alpha for all X belonging to the set In. And therefore, we can write that alpha beta X is equal to beta alpha X for all X belonging to In. This implies, by definition of commutativity, alpha beta is equal to beta alpha. Hence, the theorem says that when we consider two disjoint cycles from the symmetric group, the compositions alpha and beta, the alpha beta composition mappings are commutative with respect to the composition. Then another important theorem that I want to discuss over here is that is as the following. Not all it is not possible for me to do all the theorems, because if I do so, then the entire semester will be based upon only permutation group. Permutation group is a very big topic, so I am discussing only those important points from which I think the questionnaire can be formed, online questionnaire can be formed. So the steps of the theorem, that the theorem, as a statement, the theorem is very important. But apart from that, just don't look at the theorem and its proof as an example. You just try to get the idea of the steps, because when the question will be sent, will be formed from these topics, so it may so happen that a particular problem has been given where the steps done in these theorems may be required. So these steps are very important. So therefore, I'm choosing one or two theorems. One theorem that has been done in the previous class. This is the second theorem that I have proved over here. I'm choosing one more theorem, and after that I will write the statement of some other theorems, which you either try to prove it if you have time, or you can remember the result and I can apply it whenever it is required. My next theorem is any non-identity permutation alpha belonging to the symmetric group Sn, n greater than or equal to 2, can be expressed as a product of disjoint cycles. Where each cycle is of length greater than or equal to 2. Each cycle is of length greater than or equal to 2. So let us try to prove this result first of all. What it is saying? It is saying that any non-identity permutation. That means you already know what do we mean by identity permutation. With respect to the example that I showed you for S6, S3, the symmetric group 3, that E was the identity permutation. This theorem is only meant for the non-identity permutation. It is not applicable to the identity permutations. Okay, so we will try to prove this result first of all. Let alpha be a permutation. Let alpha be a permutation on Sn, n greater than or equal to 2. We begin by considering alpha 1, alpha square 1. Alpha square 1, I'm already, although I'm reading it as alpha square 1, it is not alpha square 1. It is alpha square 1 means first we operate alpha on 1 and then again on the image alpha is being operated. So alpha square means alpha, the composition of alpha with itself is being taken into consideration. So we begin by considering these permutations until we find the smallest positive integer r, such that alpha r1 gives you 1. This means when we consider the composition of alpha with itself r number of times, we will get 1. Okay, so that we will look for this kind of permutations until we get a permutation where for some smallest positive integer r, this is happening. This gives us a cycle, say alpha 1, so that alpha 1 is 1, alpha 1, sorry, I shouldn't put comma over here. In the cycle notation, we do not put comma. We just keep a blank space in between. So 1 alpha 1, then alpha 2 1. In this manner, alpha r minus 1 1. We are naming this cycle as alpha 1. We are not considering alpha r because alpha r1 is 1 itself. Okay. Now let I be the smallest integer in in. I be the smallest integer in in that does not appear in alpha 1. Then we can consider alpha I, alpha 2I, and so on until we come across the smallest positive integer say small s, such that alpha s of I is equal to I, and evidently this gives us an S cycle, say alpha 2, so that alpha 2 becomes another cycle which do not put comma, which is given as I, alpha 2I. In this manner, alpha s minus 1I. Remember, the previous cycle which we considered was not having the element I, it was having the element 1. And now we are considering the element I in general. So two cycles in this manner have been formed. Now, before proceeding further, observe that alpha 1 and alpha 2, as we have constructed them, alpha 1 and alpha 2 have been constructed by us. We can do the construction with respect to according to our requirement. We want to prove something. So in mathematics, these constructions which are often done are called tricks. I have already discussed this this type of tricks in discussing proof techniques in mathematical logic. So therefore, it is written that we have constructed them. So alpha 1 and alpha 2 has been formed with respect to a special rule. But according to our rule, these two cycles must be disjoint cycles. That is, we consider the elements 1, alpha 1, alpha 2, 1, alpha r minus 1, 1, and its intersection is taken with I, alpha 2i, alpha s minus 1i, gives you the null set. So there is no common element between them. Indeed, otherwise, this particular sentence means that if they are not common, what would have happened? So indeed, otherwise, if alpha pi is equal to alpha k1 for some numbers p comma k, where p lies between 1 and s and k lies between 1 and r, then we must have alpha p plus 1 I. This will be equal to alpha of alpha pi. And since we have assumed that alpha pi and alpha k1 are same, so we will substitute this as alpha k1. So we get alpha of alpha k1, and which is alpha k plus 1 of 1, and so on. And so on. And what will happen if it goes like this? Which in turn implies that alpha p plus t I will become equal to alpha k plus t of 1 for t is equal to 1 to up to, and goes on. Now, there exists some t such that p plus t is equal to s, and hence for this t I is equal to alpha s I, which is alpha of p plus t of I, which is alpha of k plus t of 1. This implies that I appears not on in alpha 1, which is a contradiction to the choice of I. So actually you can identify that this proof is about proof by contradiction. Now, if this set which I considered 1 alpha 1, alpha 2 1, alpha r minus 1 1, union I, alpha 2i, alpha s minus 1 I, not equals to in, then we consider the smallest number of in not appearing in the left hand side union above. That means is talking about this union. And continue the same process as before to construct cycle alpha 3. Since in is finite, the above process must terminate after a finite number of steps with some cycle alpha m. From the definition of the cycles alpha 1, alpha 2, ... alpha m, it now follows that alpha can be expressed as the product of the cycles, which are alpha 1 composition alpha 2 composition alpha m, product of disjoint cycles. And all of these cycles alpha 1, alpha 2, alpha m are disjoint, which actually proves the required result. I have done this proof intentionally over here. This proof is not that easy. It's a complicated proof. The proofs in permutation chapter, there are several other theorems and several other proofs. The proofs are like this. This way the proofs are actually done. Some proofs are very tedious. This particular proof is not tough, but it is a tedious proof. So I think that for your purpose, proof of the results will not be required further to study the permutation. Just concentrate on the statement of the theorem and try to implement those theorems on the in the problems whenever it is required. So I have just shown you a glimpse of 3 different proofs in the permutation chapter. Okay. Now we will try to understand this particular. We will try to understand this by an example. First of all, okay, we have written so many things on this. I mean, representation of the permutation by product of disjoint cycles. So what we actually mean by that, let us try to understand this. I think the discussion of the following example will clear your doubts. Let us consider a cycle in the symmetric group S6. Okay, and suppose I'm considering the cycle to be, I'm naming the cycle as alpha, and the cycle is like this: 2, 4, 3, 5 in S6. So under this permutation, under this alpha, the elements are moving in the following manner: 2 is going to 4, 4 is going to 3, 3 is going to 5, 5 is going to 2. And not only this, x is going to x, where x belongs to I6, difference 2, 4, 3, 5. Now we considered, say, 2 cycles. That means cycle of length 2. Such as alpha 1, say for example, it is 2, 5. Alpha 2 is equal to 2, 3. And alpha 4 is equal to 2, 4. Suppose I am considering these transpositions also with respect to the set S6. And this cycle is also there with us. Okay. Now, we shall now consider a product. We shall now form a product like as follows. As follows. What was my alpha? My alpha was 2, 4, 3, 5. My alpha 1 was 2, 5. My alpha 2 was 2, 3. My alpha 3 was 2, 4. Now we are going to consider the following product. Alpha 1, alpha 2, alpha 3 is equal to 2, 5, 2, 3, 2, 4. Alpha 1, alpha 2, alpha 3 is, this product has been formed. This product has been formed. Say, okay, all these are my formation. Now under the product, under this product, what is happening? Let us try to find out. Under this product, let us try to find out what is happening. We consider the element 2. Now, under the permutation alpha 3, the element 2, this is your alpha 3, remember. Alpha 3 is your 2, 4. So under the permutation alpha 3, 2 goes to 4. Under the permutation alpha 2, 4 goes to 4. Under the permutation alpha 1, 4 goes to 4. Why? Because in this alpha 1 cycle, 2 goes to 5 and 5 goes to 2. And as you already know that x tends to x, x goes to x if it is not falling in the cycle. So in this cycle, 4 is not there. So 4, the image of 4 under alpha 1 is actually 4. Now we are going to the first element. I have chosen 2 here because the first element of the cycle alpha is 2. Let us consider the second element of the cycle alpha, which is 4. And let us try to look at this changes which happen with respect to the permutations alpha 3, alpha 2, and alpha 1. So under the permutation alpha 3, 4 is going to 2. Under the permutation alpha 2, 2 is going to 3. And under the permutation alpha 1, 3 is going to 3. Next element is your 3 in alpha. We are actually choosing all the elements of alpha. So next element that I'm going to choose is 3. Let us start this analysis. So if I take 3, then under the permutation alpha 3, 3 goes to 3. Under the permutation alpha 2, 3 goes to 2. Under the permutation alpha 1, 2 goes to 5. Okay. Next element is 5. Now under the permutation alpha 3, 5 goes to 5. Under the permutation alpha 4, alpha 2, 5 goes to 5. Under the permutation alpha 1, 5 goes to 2. And if I consider any other element apart from this 2, 4, 3, 5, then under the permutation alpha 3, x goes to x. Under the permutation alpha 2, x goes to x. Under the permutation alpha 1, x goes to x, where x does not belong to 2, 3, 4, 5. Okay. Now, under the permutation alpha 1, alpha 2, alpha 3, that means the composition of these three permutations, what is happening? What is happening over here? Under the permutations alpha 1, alpha 2, alpha 3, what is happening is the following. 2 goes to 4, because alpha 3 will act first. So 2 goes to 4, and then 4 is going to 3, isn't it? 2 goes to 4 and 4 is going to 3, and 3 is going to 5, and 5 is going to 2. And x is going to x for the rest. X is going to x for the rest. So under the permutation alpha 1, alpha 2, alpha 3, for the elements 2, 4, 3, 5, it is happening. 2 goes to 4. Here you see 2 goes to 4. Then 4 goes to 3. Then 3 goes to 5. Then 5 goes to 2. It is coming from here. 2 goes to 4. Then 4 goes to 3. Then 3 goes to 5. And then 5 goes to 2. Because you alpha, here the alpha has been, actually what is happening? You are considering alpha as alpha 1, alpha 2, alpha 3. So first you are operating alpha 3, and then you are operating alpha 2, and then you are operating alpha 1. Right to left movement. So we can see that under the operation of composition of these three mappings, this is happening. And what is this? What is this thing? This thing is nothing but your, so alpha 1, alpha 2, alpha 3, this permutation is nothing but 2, 4, 3, 5. And what is this cycle? This is the cycle that we considered in the beginning. The cycle is alpha. So we have found that the cycle alpha is expressed as product of three disjoint cycles. So the cycle alpha is expressed as product of three disjoint cycles. Okay, and not only this, all these disjoint cycles are transpositions. Here in this particular case are transpositions. Now you see that we are able to express alpha in the following manner. So we had the cycle 2, 4, 3, 5. Any cycle of this particular form can be expressed as the product of transpositions. So the rule is that we will first write 2, and then we'll move from right to left. So we will write, first we will try to connect 2 with 5, then we'll try to connect 2 with 3, and then we'll try to connect 2 with 4. This is a formula actually. It's an example of a rule. So 2, 5, 2, 3, 2, 4 in this manner. You cannot write it as 2, 4, 2, 3, 2, 5. That will be wrong. So there is another theorem. I'm just don't panic, because I'm going to write the statement of the theorem only. Two theorems are there that you must know. I'm not going to prove these theorems, because one proof that I have done just now, I think it has already drained all of our energy to sit in this particular online class. Any cycle of length greater than or equal to 2 is either a transposition or can be expressed as a product of transpositions. This is one theorem. So any cycle of length greater than or equal to 2 can be either it is itself a transposition, or it can be expressed as a product of product of transpositions. And another theorem which is also very important is any non-identity permutation of Sn n greater than or equal to 2 is either a transposition or can be expressed as a product of transpositions. Can be expressed as a product of transpositions. Both these theorems can actually be formed or can be proved as a corollary from the earlier theorem that we have proved just now. One definition that is very important in this particular regard is this: a permutation alpha belonging to Sn is called an even permutation, if alpha can be expressed as a product of an even number of two cycles. And a permutation alpha belonging to Sn is called an odd permutation if alpha is either a 2 cycle or can be expressed as a product of an odd number of 2 cycles. So in the previous case, the permutation which we have considered over here is actually an odd permutation, because 2 cycles, the alpha has been expressed as a product of 3 2 cycles. So number of cycles is actually 3 over here, which is odd. Anyways, I am going to stop at this point. Tomorrow we have class. We are going to discuss once again something else. We'll be discussing about subgroup. So today I'm going to stop my class at this particular point. You just go through the book and try to find out what more you can find in the chapter of this permutation group. Okay, so